Thank you so much.
So first of all, I would like to thank you, Roberto, for the invitation. And my name is Marco Loche. I'm a researcher in the Czech Academy of Sciences. And today I would like to present a work that was started in the Charles University with Gianvito Scaringi that you see in the presentation. And it is about the temperature and the shear rate effects on clays. And this work has been published recently. And the idea is to present the outcomes of the presentation. So first of all, I will present in this structure a simple introduction, some methodology, the results, and the conclusions. And I would like to start the introduction with a question. And the question is why we should study the temperature effect and why they are so important. And one first consideration is that the global warming is affecting the natural equilibrium, and this is very important for in the geosa perspective, and in particular for landslides that are the focus of my research, and particularly the frequencies, the magnitude, and the pattern of landslide are changing with the global warming, and usually, to predict these climate change effects, the most common models are accounting the precipitation patterns, and on the other hand, the temperature effects are kind of not studied in detail, unless we are talking about freezing and thawing, and so permafrost environment. However, temperature is very important. Temperature is changing properties like soil strength, compressibility, viscosity, and many others. And from this point of view, we should account for the effect of temperature in slope stability, and we should even think to account temperature for future landslide susceptibility. I mentioned that we are going to study the clay materials, and to give a perspective, the distribution of clay minerals with and above the 25% is covering a large area over the globe. So the scale of our laboratory test and modeling can cover a large area over the globe. And to see in detail what we studied, we can see that we developed two main scales, and we studied two main scales at laboratory scale. We studied the residual with a modified ring shear apparatus, and at slope scale, instead we developed some slope stability model using GeoStudio and creating a subsequentially coupled thermohydro and mechanical model. To do so, we modified the ring shear apparatus to reach the residual and to change the temperature in the water bath. We studied two principal materials that are bentonite and kaolin, so low activity clay and active clay, and we expected to see three principal reaction in the residual: a positive, a negative, and a neutral effect. And we are going to see this in detail in the results that are going to plot right now. As you see, the ring shear test that we performed on bentonite and kaolin are presenting very different behaviors. These behaviors are based on different shear rates that are ranging from 0.018 to 44.5 millimeter per minute, are changing based on the normal stresses and are changing the temperature. This is very interesting and even quite complex to study. And to go in detail, I was speaking about the possibility to have positive effects, and you can see in detail, for example, for the bentonite that we studied. And in detail, we can see a positive effect, so a strengthening of the material when we increase the temperature. You can see in the graph, in the right bottom part, the temperature that is increasing from 20 degrees to around 55 degrees. And the response of the shear stress in this bentonite, a very low shear rate, is quite strong and positive. Also, we can see a really nice relationship between the temperature changes, the oscillation of temperature, and the change of the shear stress. And at the same time, we observe a positive effect in the kaolin, but a different shear rate. This is another interesting evaluation. But I mentioned before that we can have also negative effects. And another detail is about the bentonite at shear rate of 0.5 millimeter a minute. And you see that the shear rate is decreasing of 3 points with the increase of temperature, again, from 20 degrees to 55. This is very important because the decrease of shear strength can cause changes in slope stability. Similarly, we observe another weakening in the kaolin, but at different velocity, at the velocity of 0.018 millimeters per minute. Summarizing, we can see that the kaolin and the bentonite, even though are two clay materials, they behave differently. They have a kind of a reverse behavior. This is clearly connected with the mineral properties of the material. And together with this consideration, we should highlight that, for example, the friction coefficient of the bentonite is changing of around 13%, changing from 20 to 50 degrees. This is a quite significant change, and we can think to account this in some slope stability model. And we did this, obviously, and the idea was to firstly to test a simple slope stability model, not accounting the temperature, using the method of the slices and estimating the slip surface. The slip surface was estimated, and the factor of safety of this precise slip surface is 1.05. So it's a stable slope. However, this model is not accounting any thermal effect that we were studying in the laboratory. So we decided to account our next model with a general sinusoidal thermal signal. Is given us the possibility to create 4 models for every season. And we can focus, for example, on the summer model, where the factor of safety changed and reached 1.08 for the very same slip surface. However, we didn't stop here, but we create other 4 models, accounting for the most common global warming scenario, so accounting for an increase of 5 degrees. And Interestingly, we observed that the factor of safety of the very same slip surface decrease and reached the unity, making this slope unstable. So to summarize, the modeling part of our paper focus on the consideration that a model not counting the temperature is not potentially predicting properly the stability of a slope under the change of temperature that seasonally are happening, and also we account for the global warming effect, and we observe a decrease in the factor of safety that is quite important. These considerations are related to the residual shear strength, and so are very important for reactivations. Another point of view is it is interesting to see that plotting the factor of safety over the slip surfaces is showing that the majority of the slip surfaces are decreasing their value in the warm seasons that are summer, for example, and the summer that we account with the climate change scenario even more has been affected by the accounting of the thermal friction angle. Now, to summarize and conclude the presentation, I would like to highlight the contribution of this work. And first of all, I think we contributed in covering the gap of knowledge about the thermal effects and slope stability. There are not many papers on the topic. Now they are slowly growing, but when we start this research, the knowledge was really scarce about that. And we contributed in an experimental database because we tested two pure clays, and we are planning. We are currently increasing our database about thermal effects and materials. Even more, we demonstrated that the change of safety factor on clay slopes is quite evident, accounting the temperature effects. And to conclude, we think that these are quite simple application, and the experimental-based incorporation of temperature dependency can be easy to account in constitutive models and in modeling. I would like to conclude that these are the references, that these are with this list of publication on the topic. I thank you for your attention, and I'm here for any possible question.